Astronomers around the world are continuing to analyze the mysterious nature of 3I/Atlas, the third interstellar object ever observed passing through our solar system. And the more they investigate, the more unusual it appears to be. This enigmatic visitor, traveling at extraordinary speed, is currently racing past Mars, giving scientists a rare opportunity to study something that originated far beyond the boundaries of our sun's gravitational influence. Unlike typical comets we are familiar with from within our own system, 3I/Atlas displays properties that challenge long-standing assumptions about the compositions and behaviors of icy bodies drifting through space. In a recently shared but still unreviewed scientific paper, an international group of astronomers examined high-resolution data from the European Southern Observatory's Very Large Telescope, using its sophisticated ultraviolet and visual Echelle spectrograph to decipher the object's chemical makeup. The results were astonishing. The team found an extreme abundance ratio of nickel to iron in the comet's gas plume, a chemical profile wildly different from anything observed in ordinary comets or even in 2I/Borisov, the only other confirmed interstellar comet previously studied in detail. This surprising abundance pattern immediately raised questions about how such metals could exist in vapor form at such great distances from the Sun. The researchers emphasized the strangeness of their observations by pointing out a fundamental contradiction. At the distances where comets are normally observed, the temperatures are far too low to vaporize solid materials like silicate grains, metallic compounds, and sulfides that typically contain elements such as nickel and iron. In traditional comet science, these metallic atoms only appear in the gas stage when a comet is extremely close to a strong heat source. Yet 3I/Atlas displayed nickel signatures throughout all of its spectral readings, and iron appeared once the object moved within 2.64 astronomical units of the Sun. This discovery left scientists puzzled, as there is no straightforward explanation for how these metals, which would ordinarily remain locked within cold dust grains, were found freely floating in the comet's glowing coma. The analysis showed that even though 3I/Atlas is categorized as a carbon-depleted comet, it strangely behaves in a way that suggests extreme activity levels, especially in the early stages of its approach toward the Sun. Its production rates of metallic vapors and the ratio between nickel and iron were unlike anything previously recorded. Such anomalies highlight how interstellar objects can defy expectations built upon studying only local comets that formed within our own solar system's unique chemical environment. Interestingly, the researchers noted that the object's behavior might shift as it travels along its trajectory. As its distance from the Sun changes, the nickel-to-iron ratio might eventually resemble that of familiar comets. This suggests that some of the strange characteristics could be tied to its current stage of solar illumination, though it still does not fully explain why nickel was visible much earlier and more consistently than iron. Faced with these contradictions, the team proposed two primary possibilities. One is that the comet may be metal-rich, meaning its internal composition might contain an unusually high concentration of metallic elements compared to typical icy bodies from our solar system. This would imply that 3I/Atlas originated in a region around another star where the formation environment was vastly different, perhaps involving higher temperatures or a heavier element distribution. The alternative explanation is that the object's chemistry could produce metals at enhanced rates through processes not commonly seen in nearby comets. This theory connects to another previously observed oddity. 3I/Atlas has an exceptionally high carbon dioxide to oxygen ratio, indicating that jetting, outgassing, or other chemical reactions may operate differently on this interstellar object. Such anomalies continue to surprise astronomers, forcing them to rethink assumptions about how frozen bodies form and evolve in distant planetary systems. Meanwhile, Harvard astronomer Avi Loeb, known for his bold theories regarding interstellar visitors, published a new blog post commenting on these findings. He suggested that NASA should use the Mars Reconnaissance Orbiter to capture high-resolution images of 3I/Atlas as it passes near Mars, arguing that this opportunity could help scientists estimate the object's size more precisely. Loeb has previously proposed that 3I/Atlas may be significantly larger than earlier calculated estimates, possibly exceeding 3 miles in diameter. bigger than the width of Manhattan Island. In comparison, the first observed interstellar visitor, 1I/Oumuamua, was only a few hundred feet across and shaped like a flattened, elongated pancake. This stark difference in size led Loeb to raise a compelling question. Why is the third interstellar object so much more massive than the first one? The contrast suggests that interstellar space might contain a far wider range of drifting objects than previously thought, and perhaps the ones we have detected so far represent only a small slice of the true population. Despite the overwhelming consensus among astronomers that 3I/Atlas is a natural comet originating from beyond our solar system, Loeb continues to urge scientists not to rule out more unconventional possibilities. He argues that while current evidence aligns with a natural origin, the scientific community must remain open to extraordinary alternatives, including the chance, however unlikely, that the object could be a technological artifact created by an extraterrestrial civilization. Loeb has repeatedly suggested that rare or unusual interstellar objects might occasionally be engineered probes or devices sent to explore other planetary systems. And he emphasizes that discovering such an artifact would require scientists to abandon assumptions and rely strictly on measurable evidence rather than established narratives or widely accepted beliefs. In his commentary, Loeb stated that science progresses by questioning expectations rather than blindly following tradition, and he encouraged researchers to continue treating interstellar visitors as opportunities for discovering the unexpected. His call for scientific curiosity resonates strongly with the nature of 3I/Atlas itself, which has already defied numerous predictions. As the object continues its swift journey through the solar system, its behavior provides fresh data that could help reshape our understanding of the variety of materials and chemical processes present in other star systems. By studying how its metallic emissions evolve as it approaches and eventually recedes from the Sun, astronomers hope to learn more about the environments in which such interstellar travelers originate. The arrival of 3I/Atlas also underscores the importance of improving future detection methods. The first interstellar object, Oumuamua, was detected only after it had already passed Earth, while 2I/Borisov was caught earlier, but still not early enough for a spacecraft interception. Advances in wide-field telescopes and automated sky scanning systems could make it possible to identify such objects sooner, enabling space agencies to plan missions that could get close enough to gather direct samples or high-resolution images. Direct study of the materials inside these visitors could provide unprecedented clues about the diversity of planetary systems throughout the Milky Way, offering a unique window into cosmic environments that may differ greatly from our own. As 3I/Atlas streaks away from Mars and continues deeper into the inner solar system before eventually departing, the scientific community remains eager to monitor every shift in its behavior. Its composition, its metal emissions, its unusual activity patterns, and its puzzling chemical signatures all contribute to a growing sense that interstellar objects are far more varied than previously assumed. Each new observation helps refine models of comet formation, stellar system evolution, and the distribution of heavy elements in distant regions of the galaxy. Whether 3I/Atlas ultimately turns out to be simply a bizarre but natural comet or something even more extraordinary, its presence has already sparked intense scientific curiosity and opened new avenues of research. In a universe filled with countless mysteries, objects like this one serve as powerful reminders that we still have much to learn about the cosmic neighborhood beyond our sun.